Hello all, welcome to this lecture on elements of mechanical engineering. In this lecture, we are going to solve some problems that are related to hydraulic turbines. My name is Atchuta Ramacharyulu and I am working as an assistant professor in the Department of Mechanical Engineering. Now, we are going to solve some numerical problems that are related to hydraulic turbines. In the previous lectures, we have seen how the working of a turbine takes place. So different turbines are there. The working of these turbines are studied. Now using those derivations or formulas, now we have to calculate some numerical examples for the better understanding. Okay. Now the question goes like this. The head at the base of a nozzle of a Pelton wheel is 640 meters. So here we have a Pelton wheel turbine given in the question. The head is 640 meters. H equal to 640 meters. The outlet vane angle of the bucket is 15 degrees centigrade. 15 degrees. This is not 150, it is 15 degrees. 15 degrees. The relative velocity at the outlet is reduced by 15% due to friction along the vanes. So there is a loss in the friction, loss in the head due to friction, that is also given 15%. If the discharge at outlet is without whirl, find the ratio of bucket speed to the jet speed. Okay, we have to find the ratio of bucket speed to the jet speed. We have to find this ratio. If the jet diameter is 100 meters, 100 mm, jet diameter is small d, 100 mm, and if the jet diameter and the wheel diameter is capital D, 1.2 meters. Find the speed of the turbine in RPM. Okay, we have to calculate speed of the turbine in RPM and also the force exerted by the jet on the wheel. Okay, we have to calculate the force exerted on the wheel also has to be calculated, and also the power developed, hydraulic efficiency. All these things are interrelated so that we can easily calculate this. So for this we have to consider the Pelton wheel turbine, where we are going to consider the cross section of the Pelton wheel. Now I am going to show the given data here. Here H is equal to 640 meters, which is the value of the head which is given in the questions. This is all given data. And phi is the angle, the inlet angle that is present at inlet of the turbine or outlet. So 15 degrees is the outlet vane angle. So phi is the outlet vane angle. This is present here in this diagram. And VR1 is it is the ratio that is given in the question. Okay, 0.85. Here the ratio is given 15%. So this can be rewritten as 0.85. VR1 is equal to VR2 is equal to 0.85. So 15% is lost due to friction. The remaining 85% is kept as the efficiency. So that is taken as this ratio VR1 by VR2. So this is rewritten as VR1 is equal to 0.85 times VR2. So this is what written here. This one. And then VW2 is 0. So it is given in the question. The whirl velocity at the outlet is 0. VW2 is 0. And the diameter of the jet is 100 mm. And the diameter of the wheel is 1.2 meters. And CV, this is all given in the question. CV is equal to 0.97. And we have to calculate, like different values are there. We have to calculate speed, force, power, efficiency, hydraulic efficiency, and also we have to calculate Ku. Ku is nothing but it is the ratio. It is the ratio between this these two values. Okay, we have to calculate the ratio between bucket speed and the jet speed. Okay, bucket speed and the jet speed. Bucket speed to jet speed. So all these values has to be calculated. Now let us try to understand the different terminology that is related to this problem. So see here, this is the vane that is taken here for calculation. So this blue color shape is nothing but the cross section of the Pelton wheel turbine vane. Okay. Now here we have a deflection angle. This angle is with respect to horizontal is taken as deflection angle, and for with this we have to draw a imaginary triangle. So this is also called as velocity triangle because each component of this triangle represents a particular velocity, because the water that is touching the turbine, okay, initially the water will come in this direction and it will touch this point. After touching this point, it will be divided into two parts. One part will flow in this direction and the second part will flow in the bottom direction. Now there are two directions for the flow of water. As per the problem, we are considering only half part, and we will calculate the velocity to this half part and we can multiply this to get the other part also. So now, because the water is coming out in an inclined manner, it is not coming horizontally or vertically, it is coming at an inclined inclination, so that it can have two components, that is U2 and V2. There are two components of this water that is coming out of the turbine vane. Okay, they can be divided into two components. One is U. U stands for velocity of the vane. V2 stands for velocity of the water at outlet. Okay, velocity of the water at outlet. And VR2 stands for relative velocity at outlet. Okay, VR2 is the relative velocity at outlet. Now let us try to calculate some basic things like when we want to calculate velocity of the water, V is equal to CV multiplied by root over 2 times gravity into head. So CV is given in the question, that is 0.97, root over 2 times gravity 9.81 multiplied by 640 meters. So this will give you the value of the velocity 109.74 meters per second. So this is the velocity of the water that is coming or touching the blade. Okay, so water will be coming from a nozzle and it will touch the blade at the center. Okay, when we calculate this velocity, so it comes to a value of 109.74 meters per second. So far we have calculated the velocity. Now let us take the speed of the bucket as U. So U is the speed of the bucket. Okay, small u. And relative velocity at inlet. Relative velocity at inlet is taken as VR1. Here, if you want to calculate the value of VR1, we have to take VR1 from this velocity triangle. We have calculated this formula. VR1 is equals to V1 minus U. V1 is nothing but the velocity at inlet. V1 is the velocity at inlet, that means velocity of the water at inlet, and U is the velocity of the vane. The moving vane will have some velocity. So this can be calculated by substituting the velocity that now we have just calculated, 109.74 minus U. Okay, VR1 is equal to this value. And similarly, we can calculate relative velocity at outlet, VR2. VR2 is nothing but it is the relative velocity of the water that is leaving the veins. So the water, when it leaves the vane, it has some relative velocity. If we want to calculate that, we have to take VR1 multiplied by, we have a formula. We have written this because it is given in the question. 15% of the relative velocity is lost. That means only 0.85% of the, that means 85% of the relative velocity is intact. Remaining 15% is lost. So this is given in the question. So we have already written this formula. See here. So this one. This is the ratio between relative and final velocity. So relative velocities. So I am writing the same thing here. VR2 is equal to 0.85 times VR1, and VR2 is equals to, VR1 is nothing but 109.74 times 0.85. So this will give you the value around, so we don't know this value because it is not yet calculated. We know that VR1 needs U to get exact value. Okay. So now let us consider VR2. VR2 cos phi, which is equal to U. So in order to calculate U value, I am taking this equation. This equation is taken from the velocity triangle. Okay. The previous slide we can see here, this is a velocity triangle where we can write this equation. U is nothing but, so U is this one, this is opposite side, or this is adjacent side. Okay, and VR2 is the hypotenuse. So if we want to write this value, that means phi is equal to adjacent side by U2 divided by VR2. So this can be rewritten like this. Because it is adjacent side, I have taken cos phi. Okay, this is, I will rewrite this again. Cos phi is equal to U by VR2. So U is the velocity of the bucket or the vane, and VR2 is the relative velocity of water coming out of the vane. Now, by using this, I can calculate the value. Okay, so by substituting all these values, I can get VR2 is 0.85 times the 109.4 minus U cos 15. This entire value will gives you the U value, that is 49.48 meters per second. When we calculate this entire equation, we'll get the value of U. But we have a formula for velocity. Velocity of the bucket can be calculated because it is a rotating thing. We have a formula for this, pi dn divided by 60. So here pi is the standard value, and d is the diameter of the turbine runner, n is the speed of the runner. Okay, now in this we don't know some values. Here U value is known. U value is nothing but 49.48 is equal to pi times 1.2 meters multiplied by n. N value is not known. We have to calculate n value. So n value is given by this equation. So n value is around 787.5 rpm. Okay, so we are calculating one after another thing. Like we have calculated the relative velocity by using the equation that is given, and now we have calculated the speed, and now we will calculate jet ratio. So m is equal to U by V. U by V, this will value 49.48, and V stands for the velocity that is calculated 109.74. 109.74. This will gives you a value of 0.45. So this is what we got. And weight of water supplied. So why do we need to calculate the weight of water? In order to calculate the force, we need weight. So for that we are going to calculate the weight of the water here. So here we have taken gamma and Q. Gamma is nothing but it is the density of water, and Q is the discharge of water. So by multiplying these two, we can get this value like 8.62. Okay, 8.62 is the actual weight of the water being supplied per second. Okay, 8.62 kilonewtons per second. Now if we want to calculate the force, Fx is equal to rho A V1 multiplied by VW1 minus VW2. Okay, now we already know that VW1 is equal to V1 and VW2 is equal to 0. It is given in the question. VW1 is nothing but the velocity of the water entering the vane, which is equal to VW1. But VW2 is 0. Why it is 0? Because it is given in the question that the world velocity that is coming out of the water coming out of the vane is 0. Now using this, we can calculate the force. Rho is nothing but 1000. It is the density of water. And then a cross-sectional area is pi by 4 times 0.1 square. That is the cross-section area of the jet. multiplied by V1, that is 109.74 square. Finally, we will get a value of 94.58 kilonewtons. So this is the force being exerted by the water that is coming out of the jet on the vanes. Okay, now this is done. And after this, we can simply calculate work done. Simply we will multiply F times U. We will get 94.58 multiplied by 49.48. So this will give you 4679 kilonewtons per second. So this is the value of the work done per second. And from this, we can calculate power also. So if you want to calculate that, we have to calculate kinetic energy per second. So the formula for kinetic energy is half rho A V1 cube. So by using this formula, we get this value. So this is the kinetic energy per second. So this is the actual power being developed by the turbine. And also we have to calculate hydraulic efficiency. So the value of hydraulic efficiency is nothing but work done per second divided by kinetic energy per second. That means work done by the turbine divided by power developed by the turbine. So this will give you a ratio of 90.17%. That means this Pelton wheel turbine is working at an efficiency of 90%. So 90% of the energy given by the water is being converted into electrical power or just power. Okay. So we have calculated everything, like whatever the question has asked. We have completed everything, like we have calculated hydraulic efficiency, we have calculated power, and then we have calculated force, whatever the force that is being applied by the water, and then we have calculated ratio, that is jet ratio, M, and then we have calculated speed. So everything has been calculated. Now let us try to solve another example. So this is also based on a Pelton wheel. Now let us try to understand the question and try to abstract whatever that is given in the question and given data. Okay, and the question goes like this. A Pelton wheel turbine is having a mean runner diameter of 1 meter. Okay, the mean diameter is equal to 1 meter, and it is running at a speed of 1000 rpm. The speed of this turbine is 1000 rpm. The net head is 100 meters. Net head is nothing but capital H. This is 100 meters. If the side clearance is 20 degrees and the discharge is 0.1 meter cube. Okay, I will write these things. Phi is equal to 20 degrees, the angle, and discharge is 0.1 meter cube per second. And then we have to calculate the power available at the nozzle and also the hydraulic efficiency. We have to calculate power as well as hydraulic efficiency. So this is all the given data. Now let us try to solve this. So here we have to assume that CV is equal to 0.98 for the calculation purpose. It is generally taken as 0.98. If it is not given in the question, this can be considered as 0.98. If it is given in the question, we have to take that particular value. So here, when we calculate the velocity, V is equal to CV root over 2GH. So here, V is the velocity of the water that is entering the turbine or the vane. So this is calculated by 0.98 root over 2 times 9.81 multiplies head is 100 meters. So with this we can calculate 43.83 meters per second is the velocity at inlet. And again we can calculate U, that is pi dn by 60. We can calculate the velocity of the vane. U is the velocity of the vane. So pi times the diameter is 1 meter and 1000 is the RPM by 60. Here we get 52.36 meters per second. So we have got two velocities. This is V, velocity of the water that is entering the turbine, and U is the velocity of the turbine vane. Okay, this situation is impracticable and hence the data has to be modified. Clearly state the assumptions as follows. Now, here we have to assume a head of 700 meters. why we have to assume this head. So why this problem is different from the previous problem. So both the problems are based on Pelton wheel turbine, but the only difference is when we study this, okay, see here the head is 100 meters, by which we have calculated the velocity at inlet is 43.83, okay, and the velocity of the vane is 52.36. Now if you carefully observe, V is less than U, which is not practically possible. Suppose the water is coming at 100 kilometers per hour through the jet. This water will touch the turbine vane and the turbine will start rotating with a speed which will be definitely less than the 100 kilometers, okay, or 100 meters per second, because some amount of energy has to be lost due to friction, or some mechanical losses will be there, or some losses will be there in the air, etc. All these things has to be taken into consideration. But here when we compare the velocity of the water and the velocity of the turbine vane, so the turbine vane is moving very fastly when compared to the velocity of the water. So that is why we have to modify some assumptions, like H is taken as 700 meters because it is showing some error, and absolute velocity can be modified accordingly. So when we take H is equal to 700, we have modified this. Now here if we calculate velocity, CV root over 2GH. So CV is 0.98 and root over 2 times 9.81 into 700. This will give you a value of 115.96 meters per second. Now here the velocity value is above 100, that is 115. See here the velocity of the plate or vane is 52. Okay, this twice. Now this is somewhat practically possible value, so that now we can go into the actual calculation of the problem. So far we have modified the value in order to calculate easily. So see here, this is the vane and we have water that is coming out in this direction. This is taken as VR2, and then we have constructed a velocity triangle where the vertical side shows the flow velocity and the horizontal side shows, that means the adjacent side, showing whirl velocity, and the center component, it is showing the actual velocity of the water that is coming out of the jet. Now let us try to solve this by using some more formulas. So power available at the nozzle is given by work done per second. So what are the things we have to calculate when we want to, that is given in the question. So once we'll go to the question, so we have to calculate power and hydraulic efficiency. These two things has to be calculated. Now we have a very short formula here. So hydraulic efficiency is equal to, so before hydraulic efficiency we will calculate the power. So see here, power is nothing but work done per second. Work done per second is nothing but power. So in order to calculate power, we have to calculate the work done first. So work done can be simply given by rho G Q H. Here what is this rho? Rho is nothing but the density of water. This is rho multiplied by gravity 9.81 meters per second square. Q is the discharge of water that is coming out of the turbine, coming out of the nozzle. So this is also given in the question, that is 0.1, and H is the head of water that is taken now 700. So with this we can get the value of power is around 700 kilowatts. So by using a simple calculation we can do this power. Okay, so this is power, work done per second. Now if we want to calculate the hydraulic efficiency, we have a shortcut formula, like hydraulic efficiency is equal to 2 times the velocity of the vane divided by V1 square, that is velocity of the water at inlet, multiplied by V1 minus U. It is the difference of the initial velocity and the vane velocity, and then multiplied by 1 plus cos phi. This is the formula that we have obtained from the derivation, and using this we can simply calculate the hydraulic efficiency. It is the modification. So we know hydraulic efficiency is the ratio of shaft power to the water power. Okay, shaft runner power to the water power. So using this same condition, we are going to calculate this hydraulic efficiency. Here 2 times U is nothing but 52.36, which is calculated in the previous slide, multiplied by 115.96 minus 52.36. So this 115 is the initial velocity of the water when the head is assumed to be 700. Okay, divided by V1 square. V1 is nothing but again 115.96 square multiplied by 1 plus cos phi. So what is cos phi? It is 20 degrees given in the question. So this value goes to 96.07%. So the hydraulic efficiency of this turbine is 96%. So 96% of water power is being converted into runner power. Okay. Now this is the second question where we have calculated the power as well as hydraulic efficiency. Now let us try to solve another question that is based on Pelton wheel again. So the question goes like this. The Pelton wheel has a mean bucket speed of 10 meters per second with a jet of water flowing at the rate of 700 liters per second. So I will write the given data here. So U is nothing but 10 meters per second. It is the velocity of the bucket, and a jet flowing at a rate of 700 liters per second. LPS, liters per second. This is discharge. This can be rewritten as 0.7 meter cube per second. So I have simply converted this liters into like discharge meter cube per second. So Q is equal to 0.7. And then under a head of 30 meters, head is equal to 30 meters. And then the bucket deflects the jet through an angle of 160 degrees. Here phi is given as 160 degrees. Generally, the phi value stays between 0 and 40. Okay, it is not more than 40. So that is why whenever the value is given like 160 or something, more than 100, we have to subtract this value from 180 degrees because it is given on the other side of the turbine, where we can see in this diagram, if this is the deflection angle, this will be more than 100. Okay, but actual phi value will be calculated in this small triangle. So it will be less than 90. Obviously, it is less than 90 because it is a what you call right angle triangle. This value will be, this side is always 90 degrees. This phi value will always be less than 90, and sometimes it is less than 40 only. Okay. Now, from this, deflection angle can be calculated by 180. We have to subtract the 160 from 180, which will give you 20 degrees. And then calculate the power given by the water and the runner and the hydraulic efficiency of the turbine. So what are the things we have to calculate? Power, we have to calculate hydraulic efficiency. So we have to calculate these two again by assuming the coefficient of nozzle is 0.98. So CV is given in the question, which is 0.98. Now let us try to solve this by assuming the gravity to be 10 meters per second square. Here it is not taken exactly, it is taken approximate value 10 meters per second square. With this we have to calculate the power and hydraulic efficiency. Now similar to the previous problem, we have to calculate CV. CV is equal to the velocity we have to calculate, velocity is equal to CV times root over 2 times gravity multiplied by head. So here CV is nothing but 0.98, it is given in the question. 2 times gravity is taken as 10 and head is taken 30. So the value of the initial velocity of water is 24 meters per second. 24 meters per second is the initial velocity. So from this diagram we can simply write V1, which is the initial velocity. It is 24. It is horizontally moving. After it touches the turbine vane, it will be flowing in a curved path. Now in that place we have to calculate the power. Okay. Now if we take different velocities like VR1, if we want to calculate the relative velocity at inlet, it is taken as V1 minus U. So here V1 is nothing but the velocity at inlet. Just now we have calculated its value is about 24 minus U. U is the value of the bucket. So the bucket speed is given in the question. It is 10. So this will give you the value 14 meters per second. So this is the relative velocity at inlet. And then VW2. If you want to calculate world velocity at outlet, so VW2 is nothing but, before that, when VR1 is calculated, we have to calculate VR2 immediately. Here in this question, we are assuming that the turbine vanes are completely frictionless. That means there is no friction on the surface of the vane. So that is why we will take VR1 is equal to VR2. That means the relative velocity of the water before entering the vane is equal to after leaving the vane. That means there is no friction on the surface of the vane. So it is taken as 14 meters per second. Similarly, if we want to calculate world velocity at outlet, VW2, its value is VR2 cos phi minus U. So from this we can calculate 14 times cos 20 minus 10. This will give you 3.16 meters per second. So this is the world velocity at outlet. And again, if we want to calculate, so why are we calculating all these values? We have to calculate, the ultimate goal is to calculate power as well as hydraulic efficiency. So the power cannot be calculated directly. So we will always calculate work done. Work done per second will give you the value of power. So work done is nothing but rho A V1 times the world velocity at inlet plus world velocity at outlet multiplied by velocity of the bucket. So from this we can simply calculate, see here, 1000, here small modification is there, A times V1 is modified as Q, this can be written as Q. So that is how we got this value, 1000 times 0.7, that is discharge, that is given in the question, multiplied by 10, and then 10 is the velocity of the bucket, that is also given in the question, and VW1 is nothing but 24 plus 3.16 world velocity at inlet and outlet. So from this we can simply get 192.12 kilonewton meter square second. So this is the work done by the water on the turbine per second. Okay. So work done per second is nothing but the power. So we have to calculate the efficiency also. So in order to calculate the efficiency, we should need a separate formula for kinetic energy. Kinetic energy per second is equal to half times rho A V1 cube. So from this we can calculate half time 1000. Area is nothing but 0.7 multiplied by 24 square. This is square. And from this we will get a value 201.6 kilonewton per meter square. It is also cube is there, it is square. So from this we can calculate. So this is kinetic energy per second, which is nothing but it is a value which with which we are going to calculate the hydraulic efficiency. So the hydraulic efficiency is nothing but output by input. Hydraulic efficiency is equal to output by input, and this value goes to 190.12 over 201.6, and this value is about 94.3%. Now we can use another formula also for calculating the hydraulic efficiency, that is hydraulic efficiency is equal to 2U by V1 square multiplied by V1 minus U into 1 plus cos P. So using this formula also we can calculate the hydraulic efficiency. 2 times 10 by V1 is 24 square multiplied by 24 minus 10 multiplied by 1 plus cos 20 degrees. So after calculating this also, we will get the value as 94.29%, which is same as that of the general formula which can be used to calculate the hydraulic efficiency. That means output power by input power. From this we got 94%, and by using this hydraulic efficiency formula also we got the same efficiency. So the two things we have to calculate in this problem are power and hydraulic efficiency. So both of them has been calculated. Now these are all some of the numerical examples based on hydraulic turbines, and we'll meet in the next lecture. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.